The other way to approach this question is to use the contact point, marked here with a red dot, as our reference point. Now, why this solution can be a little bit more complex is because this means that there is an angle between our force and our radius, and it also means that our calculation for I must include a shift, because we are no longer thinking about the object's rotation about its center of mass. We are thinking about it rotating about this contact point. Let's take a look at how this solution works out. So first of all, when we're looking at torque, we will only use the force of gravity. The force of friction is right at the contact point, which is what we're using as our reference, as well as the normal force is right through that contact point. So neither one of those produce a torque in this case, but the gravitational force does. We will still need to make a substitution of A over R instead of alpha, because the problem does ask us to find the linear acceleration, not the angular acceleration. The angle that we'll be using is this angle right in here, kind of like we do when we just work with a mass on an incline. That is the same value, theta, as we are typically given at the bottom of the incline. So let's break this down. The distance between the start of this force, or the tail of this force, and our reference point is R, so that's this. The amount of force is mg, and then we take the sine of the angle between those two things. So that angle, again, is this little piece right in here. So that is just our theta that's given. Now our I is going to be the I for a sphere, which is 2/5 mr squared, except again that is I as if the sphere rotates about its center point. And so if we are using this point, this contact point, as our reference, we must shift that value of I. So the h for our shift would equal the radius, because we're shifting from the center to the contact point. And so we would add mr squared instead of mh squared. All right, taking a look then at our algebra, we can notice that there's an r that cancels out on the right-hand side. There's also r's that cancel out on both sides. And then there are m values that cancel out on both sides. So we are then left with g sine of theta equaling to 7/5 a. We still have to go through and do a similar type of fraction work. 2/5 plus 5/5 is 7/5, and then rearranging to find a. Now it may seem as though this problem was simpler to do than the other solution, but the key thing is that it does require us to make sure that we are thinking about that I, about that pivot point. If you don't, do this step correctly, then you really aren't understanding the subtle difference between this solution and the previous solution. But either method is certainly correct.